So the next question from the recitation worksheet is number 8. And that'd be a good time, if you haven't already tried to do this problem, to give it a pause and see if you know how to answer it. But to go for the solution, the first step that I always do in a question like this, if I sound like a broken record and you already know what I'm about to say, is I'm going to draw a force diagram. So there's two children sitting on this merry-go-round. So on this this is not a merry-go-round. On this teeter-totter are two children. They have two weight forces. So I'll call this F of kid 1, which is the weight of kid 1. We would normally call that F sub G. And here's the weight of kid 2. And down here in the middle, right here in the middle of the board, I guess there's technically two forces. We could consider the center of mass of the board, which would be a weight force that points down. And I drew that really faintly because I don't care too much about that force right now, but I guess I can draw it in. On the solutions that I'm posting, I didn't actually end up drawing that in, but there's of the board. So the center of gravity of the board is in the middle, so the weight of that board points down. There is also a normal force, which is the force of the pivot, this little triangle down here, or whatever it is that's holding the teeter-totter up, pushing up on the board. That is the thing that stops this whole teeter-totter from crashing down through the ground. Okay, so if both kids are sitting and the teeter-totter is balanced, then we must have that the torque due to this force, this kid over here, kid 1, must be equal and opposite to the torque due to kid 2. So a way to think about that is that if we think of the pivot as here, we would be able to say that it must be that the counterclockwise torque due to kid 1 is equal and opposite to the clockwise torque due to kid 2. But if kid 1 leans in, then what happens to the kid 1's force is that it will remain the same force, right? The kid hasn't lost any weight, but this lever arm here, R to kid 1, used to go all the way out to here, but now it has gotten shorter. So the torque of kid 1 is R of kid 1 times the weight of kid 1. And if kid 1 leans in, we see that R of kid 1 gets smaller, whereas the force of kid 1 stays the same, which means that the torque of kid 1 also has to get smaller. So if the quantity on the right-hand side gets smaller, then the quantity on the left-hand gets smaller too. So what we can say here is that I'm not good at my counterclockwise and clockwise. I always have to think about it. So if I have my teeter-totter here, and force of kid 1 is going to rotate it that way, which is counterclockwise. So if the counterclockwise torque from this kid 1 over here, is smaller than the clockwise torque from this kid over here, kid 2, then what has to happen? A torque is the rotational analogy to a force, and we just said that kid 1's torque is smaller than kid 2's torque when she leans in. So as she leans inward toward the pivot, she's no longer making the counterclockwise torque as big as the clockwise torque, which means that the whole teeter-totter is going to go this way. Okay, so now the torque due to this kid is bigger than the torque due to this kid. So the force that is acting to rotate the teeter-totter in the clockwise direction is bigger than the torque that is causing this thing to rotate in the counterclockwise direction. Okay, so this one beats that one, and the whole thing rotates that way. So everything starts to rotate clockwise, which means that the kid who leans inward will rise, just like that.